So thank you very much, CLIVAR Marine Heatwave Research Focus, for inviting me for this first webinar. And also many thanks for my collaborators, Eric Helen, Kristen Finder, Norman Loeb, and Oceanic, and Noah Sutton. So the heat conditions in the Earth's climate system in 2023 and 2024 were striking, with significant impact on the ocean, including marine heat waves. So this is the dates of fractions of moderate or higher marine heat waves in the global map in 2023 and 2024. So many parts of the ocean experienced marine heat waves. So in this presentation, I'd like to introduce the major feature of the exceptional global heat conditions in 2023-2024, including marine heat waves. I will also discuss our current understanding of the underlying mechanisms. This presentation is organized in the following three parts. First is global distribution of marine heat waves, and second is cause of the heat in the global surface, ocean, and atmosphere. So in this second part, I emphasize the importance of the Earth's energy imbalance. And third part is cause of the heat in the Kuroshio-Oyashio extension regions. So in this part, I emphasize the importance of the wind. So these results are taken from our papers and review. And I cannot put that information in the chat, but maybe later I can put the information in the chat. So the first part. So in this first part, I analyze the marine heat waves and the standard data, or SSD, and using a standard method following Hobday et al. The reference periods that is discussed in several papers, the reference period is important. We take the last 30 years climatology. And the other is a pretty standard 11-day windows, and moderate, strong, severe, extreme marine heat wave is determined in exceeding 1, 2, 3, and 4 times of the 90th percentile threshold. And at least this condition must last 5 consecutive days. And actually, I found the fifth threshold exceeding sometimes occurs, and I called ultra in our paper. And in order to understand the global distribution, I introduced area days fraction. So this is simply certain class of marine heat wave occurred or not. That is integrated over the Julian day and area, and divided the total area and the total Julian day in each year. So 100% indicates that class of the marine heat wave occurred 100% of the area and the days. And for moderate marine heat wave, that is generally increased in all global oceans, and blob 2.0 is outstanding in the Eastern North Pacific, but in 2023-2024 are exceptional, and that is mostly occurred in North Atlantic. So this blue line. For severe, stronger marine heat waves, that is extreme and ultra, that is outstanding in the red line, that is Western North Pacific. So this is the distribution of the global marine heat wave, moderate or higher, and stronger or higher, severe or higher, 2023 and 2024. Consistent with the previous time series, North Atlantic is very outstanding for moderate marine heat wave. And in the last years, 2028, so most of the Caribbean Sea and north of the Brazil, almost every day marine heat wave occurred. And if we look at the North Pacific, the strong marine heat wave occurred in around Japan and subarctic front, and somewhat separately in the southeastern North Pacific. And the more severe, stronger one, severe and extreme, occurred around Japan. So even the extreme marine heat wave in the last year occurred 40% of the day in this spot. So that is lasts more than 100 days. So the last year and 2023 Marine heat wave is unusually strong and prevailed globally. So second part, I'd like to understand what is the cause of these anomalous heat conditions in global oceans. So in this second part, I introduce a heat budget analysis to understand the driver's role. So we want to understand the Earth energy imbalance in the under the global warming. Earth observes more energy than the energy that returns to the out of the Earth. So this difference is called Earth energy imbalance. And the second driver is El Nino. So Earth energy imbalance hits the atmosphere and the surface ocean from the top, and the El Nino subsurface ocean heat content anomaly is transported in the near surface. So these two factors actually act to warm near surface ocean and also atmosphere. So actually, this combined atmospheric energy and near surface ocean heat content anomaly is very constantly varies with surface air temperature and sea surface temperature. So in order to understand these variables, it's very useful to understand SST and SAT. So the data we used for heat budget is cells EVAF top of atmosphere radiation and ocean heat content from combined 4 data sets, ORA S5 and 3 ocean analysis, EN 4.2, JMA, and IAP. And we analyze ERA 5 data for atmospheric energy. So this is a global summary of sea surface air temperature and surface air temperature, sea surface temperature, atmospheric energy, and 0 to 100 meter ocean heat content anomalies. So you look at a similar plot in many places, but there is a dot in these plots. So this dot is actually indicates the data are abnormal and record-breaking conditions using novel abnormal record-breaking test. That is, we introduced in our paper. In order to save the time, I don't explain what is an abnormal record-breaking test, but bottom line is abnormal is even taking account of the last 30-year trend, this data is still abnormal. So out of the expectation range. So from the 2023 summer to about 1 year, SAT, SST, and atmospheric energy, ocean heat content exhibit the condition of abnormal. So that is very unusual. And actually, these four time series highly correlated correlation coefficient is larger than 0.8. So these four time series are essentially that's different aspect of the same phenomena. And also, it is important to note that the top of atmosphere net radiation exhibits abnormal record-breaking conditions in the early part of 2023. So this is a time series of net radiation at the top of the atmosphere. And also gray is multivariate El Nino index. So net radiation increasing trend, and that is still stay positive. So that means global warming is actually accelerating. And the EI is very strong at the end of the 3-year La Nina. So that is early part of the 2023. So if we look at the atmospheric energy per unit pressure, so per unit 100 hectopascal in this color figure, in this color map, the atmospheric energy is vertically uniform in the troposphere and lower stratosphere. On the other hand, ocean heat content anomaly exhibits a marked out-of-phase variability in the top 100 meter and 100 to 300 meter. So this is associated with El Nino. In the case of the La Nina, tilted syncline means tilting westward syncline means that warm anomaly is stored in the subsurface ocean. And in the El Nino, the tilt is become flattened, then subsurface ocean, subsurface warm anomaly in the La Nina case is bring up near the surface. So that causes this out of phase conditions. Of course, global warming gives overall warming in both near surface and subsurface. So we conducted a heat budget analysis for these 3 El Nino events for 1 year period to understand what makes 23-24 exceptional. So this is the result of the heat budget analysis. The left part most bar is atmospheric energy, sorry, not AHC. So this is old terminology in our manuscript. Atmospheric energy and 0 to 100 meter ocean heat content stacked. So 0 to 100 meter ocean heat content anomaly is much larger than atmospheric energy anomalies. And the second bar is cooling in the 100 to 300 meter depths. So this acts to warm the near surface ocean. And the fourth bar is top of atmosphere net radiation integrated for 1 year period. So this second and fourth bar is driver and the leftmost bar is a target. So we can see that the target increased 50% between the previous El Nino event and present event. And El Nino relating the ocean heat movement is increased, but that is only 20% compared with 2010 and present event. And atmosphere EI increased very largely, 77%. So EI and El Nino condition is similar for the latest event, but increase of the EI is makes a difference between the previous events and present events. So we can conclude the EI that is combined with near normal El Nino that makes 23 to be exceptional. And radiation is also very important for North Atlantic. So this is a 2023 JJA. So this SST anomaly is consistent with marine heat wave pattern. And these are the heat flux due to the latent heat and surface short wave. And this is top of atmosphere short wave. So surface heat wave anomaly is stronger than the latent heat, and that is unprecedented. And this is very constant with the top of atmosphere short wave. So this is actually related to the cloud reduction. So cloud reduced and cloud reflection is reduced. Another factor is shallow mixed layer. So we consider that for the North Atlantic, combined effect of the shortwave radiation increase due to the cloud reduction and mixed layer depth decrease is important. So the third part is heat in the Kuroshio-Oyashio region. So in this part, we analyze the SST data and 0 to 300 meter ocean heat content and ocean transport of ORA S5 and wind stress of ERA 5. In order to understand the role of the wind, I analyze the swell transport. So swell transport is calculated at each grid point, and northward western boundary current transport is estimated as sine reverse zonal integration of the southward swell transport as a function of time and latitude. And the EOF analysis is conducted for the estimated northward western boundary current transport. So first we start with the SST anomaly in 1 year periods from the 2023 July to 2020 June. So the global ocean is warmed, but that temperature anomaly is mostly less than 2 degrees Celsius. But in western North Pacific, especially Kuroshio-Oyashio regions, the anomalies is exceeded even 6 degrees Celsius. So I never see such a strong anomaly before. And also, ocean heat content difference between the 2010s and the 2020s exhibit marked warming in the Kuroshio-Oyashio regions. And actually, this region is small in the global ocean. This is just 5.8% of the area fraction, but this can explain the 15.7% of the heat content increase. So this is, I think, important in the context of the global warming ocean heat uptake and redistribution. Of course, this very strong warming is associated with the Kuroshio-Oyashio changes. So this is the SST anomaly, SST difference, and this is the ocean heat content difference. The vectors indicates 0 to 300 meter depth transport difference between the 2020s and 2010s. So this arrow is identical to the arrow in panel C. Panel D is 2020s current conditions, velocity conditions. And in order to understand how Kuroshio extension varies, I also calculate the epoch averages in this region. And recent Kuroshio extension is this red one, and this is exhibit the northward shifted. So such as changes is closely associated with SST and ocean heat content anomalies. In order to understand the role of the winds, I calculate sweater transport. The yellow is climatological sweater transport estimated western boundary current. So western boundary current is northward, south of the about 40 degrees north, and south northwards, and southwards to the north. So this is corresponding to the Kuroshio and Oyashio. And near zero wind stress curve line, the estimated EOF1 of the transport is positive. So that means that if EOF1 is positive, then this can tend to push the boundary of the subtropical gyre and subpolar gyre northward. And this EOF1 of the spherical transport estimated boundary current is exhibit decadal variability shown in red. Dashed line is raw data, and solid line is a 5-year running average. So this is very closely related to the North Pacific Index, so Aleutian low. So in the recent condition is very positive. This EOF1 is associated with the weakening of the Aleutian low. And this PC1 is closely related to the mean latitude of the eastward transport between 30 to 40 degrees north, between the 155 to 160 with a 2-year lag. So definitely this wind plays an important role in the Kuroshio extension variability. A little bit offshore, so downstream of the Kuroshio extension. And also this EOF1 indicates opposite to the climatology in the subtropical gyre and subpolar gyre. So that suggests that EOF1 is positive, then that tends to weaken the Kuroshio and Oyashio. So this is actually consistent with what is found in the Kuroshio to the south of Japan. So this is JMA's analysis. So Kuroshio south of Japan is weakened recently. And also Aura S5 indicates Kuroshio in the East China Sea. It's southwestward anomaly that is opposite to the northeastward mean current, and also the northeastward anomaly in the Oyashio region, Oyashio current in the Kuril, along the Kuril Strait that is also opposite to the climatology. So this indicates recent condition is both Oyashio and Kuroshio is strongly weakened. So in order to save the time, I don't read the summary, but so marine heat wave and is very important, prevalent, and EI is important to the global warming, and Alesian law plays an important role for weakening and northward push of the Kuroshio. So lot of things to do, I think, and many new studies needed with a huge number of publications for 2023 and 2024 marine heat wave and also abnormal warming. To study these issues, international coordination, collaboration, and communication are crucial. The CLIVAR Marine Heatwave research focus will play a leading role in these efforts. Thank you very much for your attention.
Thank you so much, Shoshiro. This was a very nice presentation. And so I think, as mentioned before, we are going to move now to the second presentation, and then we'll just have a discussion on both of them. Thank you. So our next presentation is from Dr. Hirotaka Sato, and he's going to talk about the impact of an unprecedented marine heat wave on extremely hot summer over northern Japan in 2023.
Okay. So can you see my screen? Okay.
Yeah, yes. Now it's in full screen. Perfect. Thank you.
Okay. Thank you. Good afternoon, good evening, or good morning, everybody. I am Hirotaka Sato from the Japan Meteorological Agency, JMA. First of all, I would like to express my sincere gratitude for inviting me to this amazing webinar. I'm so honored to give a presentation on my recent research in front of you. I'm a forecaster in a climate prediction division in GMA, and my work at GMA is operational climate system monitoring and analysis. Today's my topic is a case study about potential local impact of marine heat wave to atmospheric heat wave in 2023, based on this my paper with my colleagues and with some distinguished climate scientists in Japan. This paper emerges from my operational work of climate system analysis and further discussions with researchers in Japan on middle latitude air-sea interactions. Recently, as you know, the active role of the middle latitude ocean to the atmosphere have attracted much more attentions in research community. So my talk is one of such studies. So I hope my talk will be of interest to all the participants of this webinar. So in 2023 summer, JJA, June, July, August, Japan experienced the hottest summer since 1898. As indicated in the upper left panel, the national average surface air temperature, SAT, was the highest, exceeding the former highest record in 2010. Furthermore, sub-regional summer mean SAT anomaly was also the highest since 1946 in the northern part and eastern part of the country. In northern Japan, record high SAT was observed every month, June, July, and August in 2023. So please see the bottom left panel. So this figure shows the horizontal distribution of JJA mean SAT anomalies in 2023. So we can see SAT anomalies is the most prominent on the east coast of northern Japan, where markedly high SST was observed to the east. And this figure shows some factors of this hottest summer based on discussions among JMA's advisory panel on extreme climate events. This panel comprised of prominent climate science researchers in Japan. So simply stated, the hot condition in 2023 summer was due to the intensified low-level North Pacific subtropical high over Japan under the significant poleward meander of the subtropical jet stream, which can be attributable to the Pacific Japan pattern and the Silk Road teleconnection pattern along the subtropical jet stream over Eurasia. So it seems natural that the atmospheric heat wave was caused by atmospheric circulation anomalies. However, a record high SST is also mentioned as one of factors here. It is not obvious that the atmospheric heat wave is influenced by the record high SSTs in the surrounding sea. So my talk focuses how the record high SSTs or marine heat waves in the surrounding seas affect the hottest summer in northern Japan in 2023. So this slide shows the data and method. I would like to skip the details, but let me see here briefly. So we use the JMA's new reanalysis dataset for atmospheric circulation and MODIS satellite data for cloud cover, and the SST and the oceanic subsurface data by JMA were also used. So in this study, climatological normals are defined as 30-year averages from 1991 to 2020, except for MODIS data and oceanic subsurface data due to their data availability. And anomalies are deviation from its climatological normal. And low-level cloud cover, as you see, low-level cloud cover are estimated from MODIS satellite data. And here clouds with top pressure higher than 680 hectopascal are defined as low-level cloud. So from now, I would like to see our results. These figures shows SST, 100-meter depth ocean temperature anomalies, and ocean currents in JJA 2023. So extremely above normal SSTs, regarded as marine heat waves, were observed around northern Japan, as indicated in the top left panel, especially to the east of northern Japan, where the Kuroshio extension and the Oyashio current confluence, here denoted as the Oyashio region east of northern Japan, OEJ. So in this region, SST was record high with about plus 5 degrees C anomalies. and so was the 100-meter depth temperature, here with about the plus 10 degrees C anomalies. These record high ocean temperatures were probably due to the extreme poleward meander of Kuroshio extension, as indicated in the bottom right panel. So where Kuroshio water was replaced with warm Kuroshio water. So this slide shows some descriptions of marine heat waves condition in OEJ region. We used the 90th percentile of SSD as the threshold of marine heat wave following the previous studies by Hobday et al. I would like to skip the details of marine heat wave definition and classification, but in the upper panel, which shows the SSD time series in OEJ, in this figure, the colored periods mean marine heat wave occurrence. So the marine heat wave event in OEJ first reached the category 1 or modest level in early February 2023 and persisted throughout the spring and summer. It developed into the category 3 and even into category 4 in August. The lower panel shows number of marine heat wave days for JJA in this region since 1985. So under the increasing frequency of marine heat wave days, the summertime marine heat wave events in OEJ in 2023 was outstanding in terms of duration and intensity. So next slide is atmospheric conditions. So upper panel shows the surface air temperature anomaly. SSD anomaly was extremely high around northern Japan, especially in OEJ, where the unprecedented marine heat wave occurred, as shown in the previous studies. The lower panel indicates the subseasonal variation of atmospheric and oceanic temperature anomalies in OEJ. It is remarkable that the while 850 hectopascal temperature, indicated by yellow color, was often below or around the climatological normal from April to July, but anomalies of SAT, SST, and 100-meter depth temperature remained positive. So this suggests that the persistent warm ocean anomalies sustained the SAT anomalies. And furthermore, the vertical profiles of summer mean temperature support this idea. The upper panel shows the lower tropospheric temperature from 1000 hectopascal to 700 hectopascal level. And the bottom panel is for subsurface ocean temperature from surface to 300-meter depth. The both figures are in OEJ for every summer, every JJA mean from 1993 to 2023. So here to emphasize the characteristics of 2023 summer, here I would like to focus 2 years, 2023, the red lines, and 2010, the orange lines. So 2010 was the former hottest summer year. The temperature anomalies in the lower free troposphere in 2023 and 2010 were the highest and comparable, but near-surface temperature anomalies were much greater in 2023 than in 2010. So this resulted in strongly reduced near-surface stratification in summer 2023. And about subsurface ocean temperature, positive anomalies in 2010 were only confined into the shallow layer above the 25-meter depth, but in 2023, they were unprecedentedly high at all depths down to 300 meters. It's due to the extreme poleward meander of the Kuroshio extension. So these features are suggestive of local influence from the marine heat wave on the extremely high summertime SAT, surface air temperature, in 2023. So how about heat exchange at surface? So I would like to give a brief overview of radiation and the turbulent heat flux anomalies at surface. The first, the solar radiation was enhanced in OEJ region. It was due to reduced low-level clouds. As I will show later, it seems because the warmer ocean decreased stability in the atmospheric boundary layer. So secondly, the upward sensible heat flux was enhanced in OEJ region. It means atmosphere was directly heated strongly by the warmer ocean, and which lead to reduced stratification in atmospheric boundary layer. And furthermore, the moisture supply was also greatly enhanced around northern Japan due to marine heat wave conditions. And lastly, the downward infrared radiation was also enhanced over northern Japan. This anomaly was likely due to increased moisture and enhanced evaporation around northern Japan, which enhanced greenhouse effect, as I will show later. So, as I said before, the low-level clouds were significantly reduced off the east coast of Japan. Usually, the low-level clouds dominate in this region in summer under the climatologically high near-surface stability over cold Oyashio water. And as indicated in the bottom right panel, there is significantly negative correlation between summertime SS day and low-level cloud cover, which indicates a cloud radiative feedback on SS day. So in 2023 summer, to the east of Japan, low-level cloud was exceptionally less than normal, at least since 2003, associated with marine heat wave conditions. In fact, at Sendai Station here, the east coast of northern Japan, the fewest fog days was observed since 1930. So these conditions suggest that marine heat wave, due to the Kuroshio extension's northward displacement, set an unfavorable conditions for low-level cloud formation and contributing record high surface air temperatures through enhanced insolation in the OEJ region and surrounding coastal regions. So another potential oceanic impact is increased moisture. In 2023 summer, as indicated in the bottom left panel, moisture anomalies were prominent by about 3 to 4 standard deviations around northern Japan. And the increased moisture acted to enhance downward infrared radiation. So precipitatable water anomalies and the downward infrared radiation anomalies, so their horizontal distribution closely match each other. So then we estimated how moisture anomalies could modify the downward infrared radiation flux under the clear sky condition following the previous studies. So the estimated enhancement was about plus 6 to 9 watt per meter square under the clear sky condition, and which accounts for more than half of the analyzed enhancement, about 10 to 15 watt per square meter. And most moisture were transported from the tropics, but there were additional local supply from the warmer oceans. So this enhanced greenhouse effect reinforced the positive surface air temperature anomalies over northern Japan landmass, as pointed out for the impact of Kuroshio large meander. So at the last of the result section, this slide shows the near-surface atmospheric temperature advection. And upper three panel shows the temperature advection anomalies at 975 hectopascal level, while net anomalous warm advection around northern Japan was primarily attributable to the anomalous southerly winds, but contributions from temperature anomalies were not negligible, around 40 to 45 degree north, and which suggests of downstream influence of the warm SAT anomalies over the marine heat wave in the OEJ region. And furthermore, to the east coast of Japan, I will just skip the details, but the core advection by sea breeze in the afternoon got weaker than normal under the reduced land-sea thermal contrast due to the marine heat waves. So our findings as summarized at these schematics for 2023 summer and normal summer. In normal summer, northeastern Japan stays relatively cool in summer due to cool onshore winds, including daily sea breeze and the reduced surface insulation by high fraction of low-level clouds or fog formed by the cooling of warm and moist air by Kuroshio water. But in extremely hot summer in 2023, the strongest warm anomaly was observed in northern Japan, where the surrounding ocean also underwent an unprecedented marine heat wave. To the east of northern Japan, the marine heat wave occurred with an extreme poleward meander of Kuroshio extension, and which is probably as internal ocean variability. This meander led to the strongest warmness in subsurface with prominent positive SST anomaly. And around northern Japan, and the positive air temperature anomalies were stronger near the surface than aloft, an indicator of the atmospheric heat wave was reinforced by the marine heat wave. The warm ocean increased upward sensible heat flux to reduce near-surface stratification and thereby low-level cloud fraction. The resultant increase of insulation acts to reinforce the high SSTs as positive feedback. And furthermore, around northern Japan, the prominent atmospheric heat wave accompanied moisture increase, partly due to the enhanced evaporation from the surrounding ocean. The resultant enhancement of greenhouse effect can reinforce the warm SAT anomalies under the clear sky condition, and which is may be viewed as positive feedback. And this is the summary, but I would like to skip the 1, 2, 3, 4, 5, first 5 bullets, same as schematics. The last point is that the process I showed here need to be validated further with qualitative analysis through numerical model experiments. But I believe that the deeper understanding of the middle latitude air interactions, including marine heat wave and atmosphere, definitely improve our operational long-range forecast. So that's all my presentation. Thank you. Thank you for my listening.
Yeah, thank you so much, Hiro. This was excellent. So I think we can now we have about 15 minutes for discussion, and we can ask questions. And I see Clara Deser already has her hands up, so please feel free to ask.
Okay, thank you so much. Can you hear me?
Yes.
Okay, very good. Thank you for these wonderful presentations. I just had a question for Sato-san.
Yep.
You mentioned the 2010
Yep.
event versus 2023. Is it correct to conclude that 2010 differed from 2023 because it didn't have a strong origin in the Kuroshio meander? Is that the difference between the two?
Yes, yes. Thank you for your question. Yeah, I think as you mentioned, the 2010, the summer condition in 2010 is totally different from the 2023. Yeah, in 2023, we can see positive active role of Kuroshio-Oyashio, Kuroshio extension. Sorry, the the we can see clear influences from the marine heat wave associated with the northward meander of the Kuroshio extension. But in 2010, the heat wave in 2010 was primarily due to atmospheric large atmospheric circulation anomalies, not from the oceans, but the primary due to the internal variability in the atmospheric sphere, I think.
Thank you.
Great, thank you. I think, Christian, did you have your hands up? Yeah.
Hi, everybody. Can you see me?
Yeah.
Okay, great. Thanks, Antonieta. Thanks for the presentations. They were very interesting. I have a question for the first speaker, Shoshiro. It's about the slide 14. I don't know if we can load that, but my question is methodological, and it's about how do you separate the contributions of El Niño and the Earth energy imbalance? Can you give me some more details about that?
Yeah, we conducted a simple heat budget analysis. And so in this context, we can separate these drivers. So as energy imbalance, just energy input from the top of the atmosphere. And the El Nino contribution is diagnosed as a heat transport from the subsurface to near surface. So this is found a simple idea. And there's the possibilities of the interaction between the El Nino and also the Earth energy imbalance. Actually, there is a publication that these two are related. And also, 3-year La Nina can influence to the Earth energy imbalance. So this is further needed to study it. Actually, Dr. Tsuchida and Yuko Sakata and me are now analyzing the CMIP6 output to understand further the interaction between the El Nino and the Earth energy imbalance.
Okay, great. Thanks.
Thank you. Alex?
Hi, everyone. Thanks for a couple of really great talks. I had a question for Shoshiro. You spoke about the North Atlantic and how it was related to low cloud cover, but also to the mixed layer depth.
Yeah.
I was just wondering, how do you distinguish between cause and effect with mixed layer depth? You know, you can have a shallow mixed layer depth that will precondition the ocean for warming, or you can have warming that shallows the mixed layer depth.
That is a great question, and we cannot distinguish the fit of speech. But from the context of the heat budget analysis, we can conclude that the shallow mixed layer depth can increase the effect of the heat input from the atmosphere to cause higher SST anomalies. But as you said, the causality is complex.
Thank you.
So before there are other questions, I was also going to ask actually both of you in different ways. I think like in Shoshiro, in your slides where you were showing the heat content or the temperature in the subsurface ocean, and there was this this increase in temperature over the years as a function of time. So clearly there is a component of global warming. And I think one question is, and in fact in both cases, one question is, what is the relative role of global warming versus kind of just internal variability? For example, even like the meanders of the Kuroshio, which can be wind-driven, as you have shown, Shoshiro. Could that also be a consequence of changes in the winds, that a trend in the winds? So how can we distinguish these two components? Because my impression is that in both cases you maybe had even a long baseline, but the data were not detrended. So I think in both results there was some climate change component.
Thank you, Antoinette. This is actually a great question. And so I consider how this additional law weakening is related to global warming or not. And actually, Brown Gann's paper published in several years before in Journal of Climate shows that under global warming, additional law will be enhanced. So the enhanced. So observed tendency is opposite to what is found in CMIP6 climate predictions. However, recent study discussed about the CMIP6 representation of the El Nino-like or La Nina-like warming is problematic. So in the observation, La Nina-like warming is observed, but CMIP6 basically predicts the El Nino-like warming. So Borangan's finding additional law weakening, additional enhancement should be associated with El Nino-like warming. However, if CMIP6 is wrong and the real global warming is La Nina-like, then additional law should be weakened. So this is a very big problem, and our climate researchers don't have the answer yet. But it is very important to conclude El Nino-like or La Nina-like global warming is actually true. And that is associated with additional law will be enhanced or weakened, and then that should increase influence to the Kuroshio-Oyashio.
I'd say. So how did Brandstater get this projection that the Aleutian law would be stronger? Was it based on theoretical arguments, or?
I think that simply estimated the changes of the sea level pressure in the end of the 21st century and the end of the 20th century in CMIP6 projection calculations.
Yes.
Sato-san, maybe you have some idea about...
You also may have some insight.
It's a very difficult question for me. I would like to know the answer of such a great question. Sorry, I don't have exact answer.
So, but is this meandering of the Kuroshio unprecedented? So this like large excursion, because the Kuroshio varies, but how abnormal or how out of the,
That is unprecedented, at least in the satellite era.
Yes.
But before that, we are not quite sure.
Yeah. Anyway, I also found it very interesting, the comparison, Hiro, that you made between the 2010 and the 2023. Because I think it was very striking, the differences in the ocean. So in one case, you have a surface warming that is due to the atmosphere. In the other case, you have an independent warming of the ocean due to the Kuroshio changes that then affect the atmosphere. So I think it's very interesting to see. Okay, are there any other questions from Alex and Clara? I think I see your hands up again. Maybe Alex, I think, whatever. We have time for both, so just one of us.
You want to go, Clara? You can go first.
Okay, yeah, I just think this fingerprint in the vertical structure of the thermal vertical structure in the ocean and atmosphere, right? That's the fingerprint of whether an ocean-induced marine heat wave, of course, with feedbacks, positive feedbacks with the atmosphere, whether that's the ultimate cause of that lower tropospheric warming and destabilization. And I think we should really pay attention to these vertical profiles in when looking at historical observations and then also in models. I think that's going to be a way forward to really take these apart. Because there's so much variability in both, but at least to get the fingerprint of what is causing, what's the maybe ultimate trigger of that lower tropospheric warming, I think one has to decompose it into these different vertical profiles. I think that would be a nice way forward. Happy to talk further with you about that.
Yeah, because also I think when you have so much, if you have like a lot of heat content in the ocean, that can, we can expect it to persist, to increase the persistence also of the atmospheric conditions. Yeah. Okay, sorry, Alex, your turn.
Thanks. So I had a question for Hirotaka. Actually a couple of questions. So one was, do you think that the large SST gradients will have had a dynamical effect on the atmosphere, changing the circulation that will play some role in what was going on? That's my first question. And the second question is it just coincidence that this, record-breaking meander in the Kuroshio happened at the same time as all these record-breaking events around the world in terms of temperature?
Thank you for your question. So the both question is very difficult for me. So for the second question, yeah, this is a very interesting question. I have never thought about such a connections. So yeah, at this time I have no idea of the origin of the unprecedented poleward meander of the Kuroshio extension. So sorry, I have no answer to the second question. So, and the first question, sorry, can I repeat your first question again, please?
So it's about the SST pattern is presumably also going to change the circulation of the atmosphere. I wonder if that dynamical effect it would have on the atmosphere could play a role in the warming over Japan.
So you mean the atmospheric circulation anomaly changed the SST?
No,
pattern?
the SST could change the atmospheric circulation.
I see. Okay. Yeah, I think there is a possibility that, yeah, not the OEJ region, but as you know, the SST anomaly, positive SST anomaly is extended from the east of Japan to the central North Pacific broadly. So you mean the SST front is displaced northward than normal in these years. So these SST anomaly can change the jet stream over the Japan to the North Pacific. I guess so, but I have no evidence or numerical experiment. So this is my speculation.
Thank you.
Yeah, I think that's potentially related, but we don't have evidence. So I examined the relation between the current and wind, and I found that wind condition is recent years is somewhat similar in what occurred in 1960s. But I believe that in 1960s, the Kuroshio didn't go such crazy latitudes. So I consider there's a possibility that another factor such as global warming play some role. And especially the heat content anomaly in the North Pacific is very rapidly increased in 2020s. And then this can be part of the ocean heat uptake and redistribution due to the accelerating global warming. So 90% of the Earth's heat uptake goes to the ocean associated with the global warming. So very rapid increase, accelerating EI means that the global ocean must take more heat and must redistribute. Unfortunately, we cannot trace down every heat movement yet. So I think that is a very important challenge for oceanography.
Thank you.
Okay, well, we are at the end of the hour, and thank you very much for, thank you again to our speaker, Shoshiro and Hiro, and thank you everybody for attending. So stay tuned for next webinars. Thank you.
Thank you very much.
Thank you very much.
Bye-bye.